Here I want to go through a few examples of some thermodynamic calculations, basically showing you a few different ways we can calculate the free energy for a reaction, the delta G. Let's take a pretty simple reaction. I don't know where my pen went to. Okay, let's take a reaction such as sodium chloride solid going to sodium chloride aqueous. Nice simple process. So we're with a physical change and chemical change. Now, if we want to measure the change in free energy, there's three ways we can look at this. I'll go to the first stage, and this is just use the delta G formation values from the tables looking up in the back of your text. And the free energy for the reaction is just going to be the sum of the free energy formation of the products, sloppy products there, minus the sum of the free energy formation of the reactants. So in this case, it's going to be, let's see, the free energy formation of sodium chloride. One of the problems you'll find here, meant to mention with this, is also, if you look in the back, you'll find free energy formation of sodium chloride solid. You will not find the free energy formation for sodium chloride aqueous. That's because sodium chloride does not exist as NaCl in aqueous solutions. So instead, what you need to look for is the free energy formation of sodium ions dissolved in water plus chloride ions dissolved in water. So you have to go back to net ionic reactions to figure out how to solve this equation, how to get the solution here, because that's how sodium chloride actually exists in solution. So that's what way it's listed. It also makes the tables more versatile because instead of having the individual ionic compounds in aqueous form, you have sodium ions, chloride ions, lithium, potassium, fluoride, whatever else, and so you can have the same table can cover many more ionic compounds that are aqueous. So it just makes it much more versatile in addition to really being more representative of the actual processes happening. So now we have to look at the free energy formation of sodium ions, and in the table it shows that is negative 261.9 kilojoules per mole. And when looking at the free energies, we also multiply this by the coefficients in the balanced equation. In this case, it's 1 mole. Again, need to stress, whenever we look at balanced equations, the coefficients normally do not tell us how many moles we have. But when looking at standard free energies or standard thermodynamic data for a reaction, we're assuming that it's 1 mole in the properly balanced equation. And again, this is why it's also critical to have a properly balanced equation in most cases, so that we can compare one reaction to the other. The only time that doesn't happen, it's not properly balanced, is when we look at the free energy formation of the products, of a given compound or element. In that case, we're assuming that the product has a coefficient of 1, so that's the only time you'll see fractions in for the coefficients for the reactants. Now, we discussed that in class. So if you have any questions about that, just ask me about it. So anyway, so plus free energy formation of the chloride ion, and that is negative 131.2 kilojoules per mole times 1 mole, minus free energy formation of the reactant. That's negative 384.2 kilojoules per mole times 1 mole, and that gives us free energy formation of let's see if I did that correctly. Go and double check. This gives us a grand total of negative 8.9 kilojoules per mole. I'm sorry, 8.9 kilojoules. Moles cancel out for this reaction. And when I did this the first time I did it, when I recorded this video, I looked at it and the delta G was actually a positive delta G. and I knew I'd done something wrong. I just mixed up the enthalpy and the free energy. It's been a careless mistake, so be careful about that. But I looked at it and knew that it could not be a positive delta G. You have to have a negative delta G for a spontaneous process, and you should know that if you put sodium chloride in water, it will dissolve. That is a spontaneous process. You stir it up to accelerate the process. That goes into kinetics, but sodium chloride is soluble in water, so it's spontaneous. So that let me know that I'd made a slight careless error there. So there are two other ways we want to look at how to solve this problem, how to find the free energy of this same reaction, just to show you for clarification. So the next way is to use this relationship. The reason I'm showing you this is you don't often have the free energy values. Sometimes also you get more information from the enthalpy and entropy values. So it depends on what you're given. So with the tables in the back of the book, these are two different ways we can figure out these values. So I just wanted to clarify this. So in this case, we need to find the enthalpy and entropy for this reaction. Delta H for the reaction. Again, we sum delta H, the formation of the products, minus sum of delta H formation of the reactants, just abbreviate RCT. So it's the same process, always products minus reactants. So this is going to be 1 mole times the delta H formation of sodium ions, which is negative 240.1 kilojoules per mole, plus 1 mole times chloride, negative 167.2 kilojoules per mole, minus negative 411.2 kilojoules per mole. Oh, sorry, times 1 mole. Gives us a grand total of thought I worked that out already. I get exactly, if I did this correctly, 4.0 kilojoules. And we'll do the same thing for delta S of the reaction. And one mole times 59.0 joules per mole Kelvin, plus 1 mole times 56.5 joules per mole Kelvin, minus 72.1 joules per mole Kelvin times 1 mole. Sorry, I forgot about that. This gives us a grand total for the entropy for this process. .4 joules per Kelvin, which of course is 0.0434 kilojoules per Kelvin. And therefore plug this in, and delta G, again delta H minus T delta S, temperature we said is 298 Kelvin. Actually I didn't specify that up top, but we need to know that it's at 298 Kelvin. Otherwise we can't solve this. So I just put up here at 298 Kelvin, something I should have mentioned previously. So in this case, it's going to be 4 kilojoules per mole minus 0.00434 times 298. Gives us 2.7 . Oops, sorry. (2.7 kilojoules), which is different than negative 8.9. So again, I know I've done something wrong here. We'll double check the values that I put in, because this should be, it really has to give us the same value that we had previously. So I put in something incorrectly. I'm going to pause the video and go find out what the issue is. Let's see. Okay, I'm back and figured out my error was a calculator error, so something else for you to be careful about. When I recalculated, I had actually messed up the entropy for some reason. I'm not sure what I did, a keystroke error in my calculator. Again, I knew that delta G could not be positive, so for this process, since salt is soluble in water, and the answer we get actually is negative 8. Oops, if I can write today, negative 8.96 kilojoules, which is the same as we had up here, so it should be the same value. So again, that's the point. We do from two different methods. We can actually figure out the entropy, the free energy. If we have delta G values, that's the simplest way, at least the quickest way, at a given temperature. For delta H values, if we have delta H and entropy values, then we can use those. You can often correct for enthalpy and entropy with temperature, so sometimes these are more useful in looking at different temperatures outside of 298 if you don't have tables available. All right, one more time, trying to get this to work without crashing my computer. I'm not sure what's been wrong. Anyway, the third way I want to show you how to solve for the free energy is using two different equations. We may not always have access to tables of all the free energy and enthalpy and entropy values that we need. So if we let's rewrite our initial expression. Sodium chloride goes to form sodium ions, aqueous, plus chloride ions, aqueous. So suppose we have two other equations. We don't have access to tables, but we're given two different equations. We're given solid sodium plus elemental chlorine, gas phase. This actually has a 1/2 coefficient. I'll explain that in a second. Forms NaCl solid, and we know that the delta G for this reaction is, let me recalculate that, I think I wrote the wrong number down. This is negative 384.2 kilojoules per mole. And I want to point out, this is why this is about the only case where you'll see a fractional coefficient in a balanced equation, because really what this is the free energy of formation. So it should be an S there. It looks like a subscript 5 or something. But anyway, NaCl solid phase. You'll have fractional coefficients for the energies of formation or heats of formation or entropies of formation for the given elements or compounds. That's the only time you have fractional coefficients, because it's assuming the energy to create 1 mole of that compound or element. That's the only time fractional coefficients are allowed. And we also have another equation. Again, these will be given. Sodium chloride solid plus, we'll have chlorine gas phase goes to form aqueous sodium chloride plus aqueous chlorine, and delta G in this case will be given as, let me add that up. In fact, I'm going to change this to have this written properly, just to show you the rules here. This is not free energy formation. So for this reaction, the way it's written, it should be negative 786.2 kilojoules per mole. And so if you look at these reactions, call this reaction 1, this is reaction 2, and this is just examples of reactions you may be given to sort of show you how we add reactions together to get our thermodynamic values for a new reaction. If we compare the reactions, we need to decide how do we combine these reactions to get our desired reaction. So over here we have sodium and chloride ions as the products. That's what we have up top. So that's what we want. The problem is coefficients for these guys are 2, where we need coefficients of 1. We also have sodium chloride solid here, which is what we want, but that's on the wrong side. So we need to rearrange these guys. And this is what when we look at how to rearrange them, let me rewrite equation 3, which is really just the negative of equation 1. We'll flip it around. So this is NaCl solid, goes to form sodium solid plus, it should be 2 there. We'll have chlorine gas, and delta G of this reaction, since we flipped it around, is now plus 384.2 kilojoules per mole. Equation 4, I see right here, equation 3 is just negative of equation 1. Equation 4, we're going to have this as, since we need to reduce coefficients of the sodium chloride ions in equation 2, we really want to have this as 1/2 of equation 2. So we're going to have sodium solid plus chlorine gas, and I need to make this 1/2 like we had to begin with. Goes to form and delta G here is going to be negative 393.2. Oops, also pen. And now we just add these up. Will be really the delta G of reaction 3 plus delta G of reaction 4. If you want to verify that, you might want to add these two reactions together, and the elemental sodium and chlorine cancels out, so we're left with our initial reaction, which is what we're trying to get to. And add this up, and we should get the same value we had. And it is negative 8.9 kilojoules. Well, kilojoules per mole, when you add it up explicitly, moles cancel out. So that's what we get. So again, 3 different ways you can get to the same problem, or get to the same solution. So you need to keep this in mind depending on what information you're given, what information is at hand. You may need to use one of these methods to reach your solution. For the same reaction, let's calculate at what temperature range is this reaction spontaneous? Go through the same things we've been looking at. So to find temperature, we need to use delta G, delta H minus T, delta S. We need to use these values. To find the different temperatures, we really have to make a big assumption. We have to assume, at least for now, that the enthalpy and entropy are independent of temperature. That's not exactly the case. But it's a first approximation. There are ways we can correct for the temperature dependencies. For right now, want you guys just to keep it simple, and we'll assume that they're independent. Entropy is not as dependent as enthalpy is not as dependent on temperature as entropy, but they do actually both vary with temperature. So assume for the purpose of this argument, delta H and delta S are temperature independent. So basically we want to find the point at which delta G equals 0, the temperature at which delta G equals 0, because that's our inflection point. Delta G is negative, spontaneous. Delta G is positive, not spontaneous. So we want to find out the point at the temperature at which this reaction goes from spontaneous to non-spontaneous. So this is a good exercise in how to apply this process, this equation. So therefore we get 0 equals delta H minus T delta S, which means that if you rearrange this, you may want to pause and check your algebra. T, of course, is going to be delta H over delta S. And the delta H that we calculated, let me redo that because my computer crashed. And I get 3.9 kilojoules per mole. Actually, it would be kilojoules in this case. The entropy would be 59. 43.4, and that's going to be, of course, 0.0434 kilojoules per Kelvin. So we get 89.9. Kelvin is our inflection point. So we need to decide, is the spontaneity above or below this temperature? It's not at this temperature necessarily. This is the inflection point where we actually have no reaction. If delta G is exactly 0, it doesn't proceed in either direction. So we have to look at delta H, T, delta S. For delta H to be negative, go back to our initial expression, go back to this relationship. We know that delta H and delta S are both positive. For delta G to be negative, the delta S has to dominate. It's only going to dominate more at higher temperatures. Therefore, this relationship is only going to be spontaneous if temperature is greater than 89.9 degrees Kelvin. So this shows you how we can apply thermodynamics to figure out at what point we may become more or less spontaneous. Again, this is still a very rough approximation because delta G and delta S are temperature dependent. Lowering the temperature by a couple hundred degrees, definitely they're going to be affecting those values, but at least gives you a first order approximation on how to do these calculations. So hopefully that gives you some assistance in performing some of the basic calculations. Again, let me know if you have any more questions.